Okay, good morning, everyone. How did those series go with you? Any questions from the homework? I'll give you a minute till everybody connect. Ooh, 41, 42, and 59. Okay, so we look at those problems and then we move on. So 41. So basically all of them, everything we will do will be based on the following power series. So if you take the function f of x equal 1 over 1 minus x, this can be written as the following series, 1 plus x, and it's derived from the geometric series, and so on. It means sigma x to the n equals 0 to infinity. And this equality holds as long as x is between -1 and 1. It means if you plug in any value of x between -1 and 1, whether you plug it in this expression of the function or you plug it in the expression of the series, the specific values, then the limit of the partial sum of the series will be exactly equal to the value of the function at the given point. Now, based on this, we will do some problems. So let me look at 41. Okay, 41. So that's a typical scenario where my function is 1 over 1 minus 3x. And the question is, find the power series representation of that. So as we did yesterday, we're going to substitute 3x for x. Okay, in the geometric series. Okay, we're gonna do that. So this will give me 1 plus 3x plus the quantity 3x squared plus the quantity 3x to the power 3 plus etc. So in sigma notation, that would be sigma n equals 0 to infinity. Instead of x, I'm going to put 3x to the power n. And now always we have to watch the domain, the interval of convergence. This equality holds as long as what I substituted, it means as long as the 3x is between 1 and -1. Okay, that's really the condition. Question? Okay. So now we just have to simplify a little bit. So this will be written as 1 plus 3x plus 3x squared, 3x times 3x, so it's 3 squared x squared, 3 cubed x to the power 3, we're simplifying, and this would give me sum n equal 0 to infinity of 3x to the power n, 3x times 3x times 3x n times. It means it's the 3 to the power n x to the power n. X between -1 and 1, I mean 3x between -1 and 1, it means that give me x has to be between 1/3 and -1/3. So this equality will hold as long as x is in here. End of the problem. Okay. So what this piece represents is actually the interval of convergence of the series. It means if you take this series, try to find where it converges, we're going to have between -1/3 and 1/3. Question as I move on. Let's look at number 42. It's g of x equal x to the 3 over 1 minus x. All right, everyone, everything we're doing in those problems is we have to relate them to the original series. We have to relate them to them. All right, this one we will do exactly what we did yesterday. We have to rewrite to be able to relate. We're going to rewrite it as x to the 3 times 1 over 1 minus x. Now we know 1 over 1 minus x. We're going to multiply across by x to the 3 and we will be done. So let us write the expression. So g of x would be x to the power 3 times 1 over 1 minus x is a 1 plus x squared plus x cubed, etc. It means x cubed, this could be written as sigma x to the n equals 0 to infinity. And this holds for x between -1 and 1. I didn't make any substitution here. It's only 1 over minus x. So this series converges between -1 and 1. And now I just distribute. This is just a sum. So I'm going to distribute the x cubed both here and with respect to the general term. So this will give me x to the power 3 plus x to the 4 plus x to the 5, x to the 6, and so on and so forth. This is equal to sigma n equals 0 to infinity. At this stage, what we're going to do is we're multiplying every term by x to the power 3. That's what I'm doing here. So this will give me x to the power n plus 3. That's really what this is happening. So every term we're distributing, like I distribute here, each one is multiplied by x3. That's give me x to the power n plus 3. And this goes again, x between -1 and 1. So that's my power series representation. So basically what we're doing is actually taking a function like that and viewing it as polynomials. I mean, we're trying to view it as a polynomials. If I take only the first term, I get a good approximation by a polynomial. If I take the second two terms, I get a better approximation and a better approximation. But this approximation works when x is between -1 and 1. Means if I'm outside -1 and 1, the approximation totally fails.
I have a question.
Yes, please.
So what is it called? Like the boundaries when it's like -1 to 1, that likely won't change when we're just dealing with powers, like in this situation.
Because we did not, because we kept x, so we don't have to x.
Yeah, it's the same. Once we switch,
it has to be the
same.
X. Yeah.
Okay.
Because we're not substituting basically anything for x. This is just my typical geometric series, which converge between -1 and 1.
All right. Thank you.
Okay. So now let us finalize this with number 59. This doesn't work anymore. And here we are. What is 59 about? F of x equal 3 over 3 plus x. And the question is, I mentioned this, find the power series and give the interval of conversions. All right. Okay, so how are we going to rewrite this? Remember, we have to relate it to the series we know, which is 1 over 1 minus x and 1 over 1 plus x. Both of them could be used. So since there is a plus here, I'm going to relate it to the 1 over 1 plus x, which is, as we saw yesterday, it's like 1 over 1 minus x, but it alternates. It means sigma -1 to the n, x to the n equals 0 to infinity. And this one holds between -1 and 1. So that's really what we're going to relate it to. All right, now back to you guys, how you're going to rewrite this to relate. Now I'm listening to you.
Would we rewrite 3 over 3 plus x as 3 times 1 over 1 plus x?
No. Is this the same as that?
Oh, no.
Absolutely not. I'm not changing, I'm rewriting. So this has to go. We have to do better than that. I'm rewriting. Be very careful. You're not changing a word. Go ahead, ideal. I know that you know. I did that yesterday.
Numerator and the denominator by 3.
Divide numerator, denominator by 3. We can do that. So if I divide this by 3, I get 1. Divide this by 3, I get 1 here plus x over 3. So we can do that exactly. Or if I want to follow Chris, what your classmate said, because there is a coincidence, 3 and 3. They don't have really to be 3 and 3. I mean, I can give you 4 and 3. So that's why I'm going to do it without dividing. So how are we going to do this? I cannot do it 1 plus x. Basically, I'm going to factor out the 3. And this would leave me with 1 plus x over 3. Have I changed anything? That's crucial. Am I changing the expression between those two? Yes or no?
No.
No. So I'm still safe. Now, this is going to give me 1 over 1 plus x over 3. So now I'm very much like the previous term, okay, which is equivalent to divide by 3 numerator and denominator. At this stage, I'm actually safe. So now we're going to substitute x over 3 for x in the power series of 1 over 1 plus x. And now let's do that. So I have my function f of x equal. So we're substituting x over 3. So it's become 1 minus x over 3 plus x over 3 squared minus x over 3 cubed plus etc. And in sigma notation, we will get sigma n equals 0 to infinity of minus 1 to the n instead of x is x over 3 to the n. And now this will hold, since I substituted x over 3 for x, this will hold when x over 3 is between minus 1 and 1. Now the rest is algebra, making things look actually much better than that. So now finally we have f of x equal the following: 1 minus x over 3 plus x over 3 squared is x over 3 times x over 3, which will give me x squared over 3 squared minus x cubed over 3 to the power 3, and so on. This equals sigma n equals 0 to infinity of minus 1 to the n x to the n over 3 to the n. And now the domain, the interval, x over 3 between minus 1 and 1 multiplied by 3. It means this equality holds if I take x between 3 and minus 3. It means this equality works between minus 3 and 3 and fails otherwise. Okay. All right. So what we're going to see today is the following. We wrote a lot of function as a power series, or if you want to think about it as polynomial. But the question, and every series, every function we did, we had to relate it to 1 over 1 plus x or 1 over 1 minus x. That's really the only way we can do it. Now, what if I have a function that I cannot relate, like e to the x, or sine x for that matter? There is no way I can relate e to the x to 1 over 1 minus x, or to 1 over 1 plus x. So the question is, how can I write this function as a series? And that's the idea, that's where the Taylor polynomial are gonna come back to the picture. So let us a little bit go back and share with you the idea of Taylor polynomial. Now we've practiced how to find the Taylor polynomial of functions. So if I find function e to the x, and I try to find its Taylor polynomial at x equal to 0, I will do it very quickly. You guys don't have to write because we're going to do that again. So f of x equal to e to the x. It means f of 0 is 1. F prime is e to the x. So I'm starting with a very easy one. So, and of course, as we realize, all the derivative. So the second derivative at 0 is 1. So if I think of Taylor polynomial at 1, so the first degree will be 1 plus x. The second degree will be 1 plus x plus 1 over 2 factorial x squared. The third degree is going to be this one. And the fourth degree, we add more to. And let us share again what's happening on graphically for that. So if we share the screen, just let us see again what's really happening, which one this is. That's Taylor polynomial. All right. So, sorry. Okay. So that's the function e to the x equal to 0. If I take the first degree Taylor polynomial, which is the 1 plus x, that's the tangent line, and that's the approximation it makes. If I take, as we've done this before, if I take 2, we have a better approximation, and this is near 0. So the center, a equal to 0, tells me that the approximation is very good near the center, a equal to 0. Now, if I keep taking more higher degrees, we get a better approximation, and it's on a larger interval. So remember, n equal to 2, the approximation is very, very close to 0. When we take n equal to 3, the approximation is actually getting over a larger interval. And then if I keep going. If I take n equal to 7, I have even a better approximation. I mean, and it's over a larger interval. So that's n equal to 5. So this is n equal to 5. It means 5 degree Taylor polynomial. When I'm taking n equal to 7, we'll approximate ex is the green one, and the red are those polynomials. We have a better approximation. If I keep moving, we have a better approximation, and over a larger interval also. It means if I plug in x in this polynomial, and in the 10th degree order polynomial, and in the function, the values are going to be very close to each other, and they're going to be very close, according to this picture, somewhere between -4 and 3, because after -4, the approximation is not very good. But if I keep taking higher degrees, the approximation are getting better for a larger interval. Higher degree, the approximation is better. Higher degree, the approximation is better. So what this is going to suggest is the following. If I take the following series, if I take the series whose partial sums are those Taylor polynomial, this series is going to approximate the exponential function very well. So what we're trying to say here is that the power series that will approximate the function, the power series that will give me e to the x, is going to be the series whose partial sums are the Taylor polynomial. This series will be given a name, and it will be called the Taylor series. So the series that approximate every function will be the series whose partial sums are exactly the Taylor polynomial. Okay, so we're going to introduce today the idea of Taylor series, and Taylor series will be the series that will approximate any function we want. All right, so let me introduce the idea. Any question before we move on? All right. So Taylor series, I'll give you enough time to write these things up. So section 11.3, Taylor series, and this will tie the power series to Taylor polynomial. So suppose you have a function, f of x, and this function is infinitely differentiable on an interval centered at a point A. Infinitely differentiable means the first derivative, the second derivative, the third derivative, all the derivatives exist on an interval centered at A. So we have lots of derivatives. Then the Taylor series of f, so that's the new word. So we saw Taylor polynomial, now Taylor series. So the Taylor series of f centered at A is basically the series whose partial sums are the Taylor polynomial of f. So the Taylor series it's a series, so it means we keep adding, but its partial sums are the Taylor polynomial. What does it mean? That is, the Taylor series of a function at a point A is the following series. The partial sums are the Taylor polynomial. So f of A plus f prime of ax minus a, the tangent line, plus f double prime at a over 2 factorial x minus a squared. That's what we call the quadratic approximation. Plus the third derivative at a over 3 factorial x minus a to the power 3, plus etc. In the series, we don't stop. So we keep taking more and more term, because the idea is that more term we take, the better the approximation. So the Taylor series, so in sigma notation, it's sigma n equals 0 to infinity, the nth derivative at a over n factorial x minus a to the n. So the idea that if I have a function and I want to approximate it by a series near a point A, I am going to use the Taylor polynomial, the Taylor series at A. You guys done? Can you move this paper up a little bit? Is it better, Elizabeth? Okay. I mean, it's actually in your book. So suppose a function is infinitely differentiable. The Taylor series is the series whose partial sums are the Taylor polynomial. So it means what I'm writing here are basically, we're familiar with that. So those are the Taylor polynomial, but we keep adding. So we don't stop at any degree. We keep adding more and more and more. Can I move the paper? Yes or no? All right. All right. Now, there is a theorem. The theorem tells me the following. So the theorem below holds for most of the function we encounter in calculus. So we're not going to prove them, but we're going to accept the theorem. So it tells me that every function that we're familiar with in calculus, what do I mean by that? Ex, cosine x, ln of x, those are the basic function we work with. Every function, as long as all the derivative exists near A, every function is equal to its Taylor series. It means if I find the Taylor series, I plug in a value in the Taylor series, value in the function, we have the same number. So f of x is equal to its Taylor series. And the equality holds for all values of x where the Taylor series converge. So every function, it's equal to its Taylor series, but the equality works when the series converge. So when the series stop converging, the equality totally fails. So I'll give you a minute to write this down before we start the examples. And this will be eventually the power series of any function we want. So if I have a function, if I cannot find its power series by manipulating 1 over 1 plus x, this is the formula for the power series of any function that we want, most of them. And now here I'm saying the equality holds whenever the Taylor series converge. Finally, a note. If A is 0, it means if I find the Taylor series, Taylor polynomial at 0, so f of 0, f prime of 0, x, and so on, then the Taylor series is called, it's just a name, Maclaurin series. So Maclaurin series is the Taylor series, but where the center is A. So the Maclaurin series would become the following. So that's the Maclaurin. F at 0, so that's the Maclaurin series, plus f prime at 0x plus x squared plus the third derivative at 0 over 3 factorial x cubed. So that's really what we mean by Maclaurin. So A is 0, that's all. And the reason we have two names is because, theorems and ideas are after people came up with ideas. And the idea of the Taylor series was due to two people. One is called Taylor and one is called Maclaurin. So the decision was that, okay, the general one, we give it the name Taylor. And to give credit to Maclaurin, we're going to give him the name for the power series at 0. So it's just giving credit to the people who came up with those ideas. over n factorial x to the n. Now we're going to start working with those series. Can I remove the paper? Yes or no, everyone?
Yeah.
Yes? All right. Good. So now we're going to go back to e to the x, and we're going to find its Maclaurin series, all of it, and then its interval of convergence. Okay, so where it means for which value of x does the equality hold. So let f of x be equal e to the x. So question number one, so we're going to do a lot of examples. So question number one is, find the Maclaurin series of f. In other words, Taylor series at x equal to 0, at a equal to 0. That's the one I did a minute ago, so I can go through that very, very fast. So we know that f of x is e to the x. It means its value at 0, it's 0. F prime is e to the x. F prime at 0, my apology, it's equal to 1. Now the second derivative again, so that's what makes this series very easy. The second derivative at 0 equal to 1. So etc. All the derivative at 1 because the derivative is not changing. So this tells me that the Taylor series is, which is e to the x, is equal to 1. And this is one of the most important, actually, power series. 1 over 2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the power 4 plus so on and so forth. It means this is equal sigma x to the n over n factorial and equals 0 to infinity. Now, question number 2 is, the theorem tells me that the equality hold. It means if I plug in a value of x in this series or a value of x in e to the x, we get the same answer for all x in the equality hold for all values of x where this series converge. So my question number 2 is the following. Find the interval of convergence. The interval of convergence of the Maclaurin series of f, of e to the x. I mean, this is a series. For some x's it converges, for some x's it diverges. And the question is, for which values does it converge? And this equality will hold for every value where the Maclaurin converge. So let us remember how we found the interval of convergence. So here my an is xn over n factorial. An plus 1 is xn plus 1 over n plus 1 factorial. And how we find the interval of convergence? We take the ratio, and then we ask ourselves which x's make the ratio less than 1. So if we do the ratio here, a to the n plus 1 is going to become x to the n plus 1 divided by the quantity n plus 1 factorial. Divided by an is like multiplying by the n factorial over x to the n. So it's mean equal to as n tends to infinity of. Now, as usual, we put like term together. N plus 1 factorial is n factorial times n plus 1. And this is x to the n times x over absolute value of x to the n. Now, those simplify and those simplify. And this will give me the limit as n tends to infinity, absolute value of x over n plus 1. Now, when n goes to infinity, this whole thing will go to 0. So the ratio is equal to 0. What does this tell me? So I have this series. I find the interval, I'm trying to find the interval of convergence. I get a ratio which is equal to 1. What does this mean? The ratio, sorry, I got the ratio equal to 0. What does this mean?
It has an infinite interval of convergence.
Right. This is less than 1 for all x. It means that the series converges for all values of x. What does it mean for us? For us, it means the following. That it means the following. E to the x is equal to this sum the equality hold. So the theorem tells us the equality hold for all values of x for which the series converge. This tells me that e to the x is always equal to that for all x. Means that if you plug in any value of x, whether you plug in 100 here or 100 here, we will have equality. The only issue is, if you take a value close to 0, you need few terms, the first probably 3 terms to estimate or approximate e to the x. If you take large value, eventually you will approximate e to the x, but you need a lot of terms from the power series. Okay, so that's the power series of e to the x. As I said, that's one of the most important power series you will ever encounter. E to the x, sine x, and cosine x, that you're gonna go do all of them. All right, before I move on to sine x, I'm gonna add another question. 1, 2, 3. ABC if you want. Find the power series representation of f of x equal e to the 2x. Okay, and you're gonna do it in 2 ways because I'm gonna explain a point. Right. We've mentioned 2 things. We've mentioned the power series representation in x. We talked about power series representation and Maclaurin or Taylor series. They actually mean the same thing. Both of them mean taking the function and writing it as a series. How to write a function as a series is immaterial, how we write it. Whether we write it using the Taylor polynomial or we write it using the manipulation that we did in the previous section, the answer will be the same. So what I am talking about. Find the power series representation in x of f of x equal to dx in 2 ways. First, using Maclaurin series. That's the first way we're going to do it. Okay, first by using the Maclaurin series. What I am talking about Maclaurin series means the following. I have the function e to the 2x. So f of x equal e to the 2x. So if you use the definition, it means I have to evaluate all those terms and plug them in. So we will do that. So we have f of x equal e to the 2x. It means f of 0 is equal to 1. F prime is 2 e to the 2x by the chain rule. It means f prime of 0 equal to 2. Now the second derivative at x equal 2 times 2 e to the 2x. It means the second derivative at 0 is equal to 2 squared. The third derivative is 2 squared times 2, e to the 2x. It means the third derivative at 0 is 2 to the power 3. And I can keep going, but of course a pattern is emerging. So what is the nth derivative of x? What's the pattern?
2 to the
2
n.
to the n power.
Exactly, 2 to the n power e to the x. It means the nth derivative at 0 is, sorry, e to the 2x is equal to 2 to the n. Right? So smell me that. The function e to the 2x equal to, using the formula, 1 plus f prime at 0 x plus f prime at 0 over 2 factorial x squared plus the third derivative over 3 factorial x cubed plus so on and so forth. And this is equal to, in sigma notation, n equals 0 to infinity of. The nth derivative is basically 2 to the n over n factorial x to the n. So if I use Maclaurin, it means that if I want to write e to the 2x as a power series, that's what it is. And this will show you can do the interval of convergence the way I did it a minute ago, and this holds for all x. I will not repeat it, but this, if we find the interval of convergence, this will hold for all x. Okay, so that's one way to do it. So that's how we can write e to the 2x as a power series. Now, I'm going to do it in a different way. And my goal is to show you that when you're asked to find the power series, we may find it, there are different ways of finding it, but all give us the exact same answer. So we don't have two different power series of a function. All right, the second way is the following. What do you think is going to be the second way? So I'm going to write e to the 2x as a power series in two ways. One, using the formula, and another one, do you think, is what? Okay. The other one is, if I know e to the x, and I want e to the 2x, I only need to substitute 2x for x in this expression, and then I will have it. So the second way is by substitution. By substituting 2x for x in the power series or Maclaurin series, they actually mean the same thing. In the power series or in the Maclaurin series of f of x equal ex. And the idea is that it's one of them. There are not two of them. They all give me the same answer. So let's do that. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. And it's sigma x to the n over the n factorial n equals 0 to infinity. And this holds for all x. And we proved that. So I'm going to substitute 2x for x. Means whenever we have x, I'm going to put 2x. I will have 1 plus 2x plus 2x squared over 2 factorial plus 2x to the power 3 over 3 factorial plus so on and so forth. So it means sigma. Instead of x, 2x to the power n over n factorial from 0 to infinity. And since this holds for all x, even substituting 2x, nothing will change, and this is for all x's. So now I'm going to streamline this a little bit and convince you that it's the same thing as that. These are exactly the same idea. So this is 1 plus 2x plus 2x squared is 2 squared x squared over 2 factorial. 2x to the power 3 is 2, 3, x3 over 3 factorial. which is exactly the same as we're getting before, plus etc. So in sigma notation, it will be 2 to the n, x to the n over n factorial. And it holds for all x. Okay. So writing a function as a power series, now we can do it using Maclaurin or Taylor series, the formula, which is this one. So we can either do it using the formula. If I cannot relate my function to anything I've seen before, if I can relate it to something I've seen before, I can use the idea of a substitution to find the Maclaurin. Either way will give me the exact same answer. That's really the same thing. Those will end up being the Taylor polynomial, those partial sums. Now we're going to do other functions. And please, if I'm going fast, let me know. So now we're going to do example number 2. Again, find, I'm still working with Maclaurin because those are the most basic series you'll ever encounter. Find the Maclaurin series of f of x equal sine x. Okay. So find the Maclaurin series of the function f of x equals sine x. So we're going to do it. So this is f of 0. I'm rewriting it again. So to give us an idea, x plus over 2 factorial x squared plus the third derivative at 0 over 3 factorial x cubed plus etc. So that's the series. So to find it, and sine x, I cannot relate it to anything. I cannot relate it to e to the x or 1 over 1 minus x. So I definitely have to use the definition itself. X to the n. So that's the formula. Now we're going to use it. All right. So f of x equal sine x. I need f of 0. So f of 0 is the sine of 0, which is equal to 0. So I have to keep finding derivatives. And when you think I should stop, you tell me to stop. So it's up to you to tell me, or I will keep going forever. F prime, derivative of sine, is the cosine. It means the derivative at 0 is the cosine of 0, which is 1. So I'm finding, at this stage, I'm finding basically the tangent line. Now the quadratic approximation. The second derivative at 0 is minus the sine. It means the second derivative at 0 is the minus sine of 0, which is equal to 0. So the coefficient here is going to be equal to 0. Now the third derivative. Derivative of sine is cosine, so I will have minus cosine. It means the third derivative at 0 is minus the cosine of 0, it is minus 1. So now I found the, if you want, the cubic approximation. Now I'm going to keep going.
Can you stop? Can you stop now?
Can I stop now? Yes, because.
I mean, I guess I don't have like a good reason. I just feel like 3 has been enough for every single other one.
Doesn't it keep switching? Isn't it 0, 1, 0, negative 1, 0, 1, 0,
Yeah.
negative 1?
Right. That's really the main reason why I feel comfortable stopping. Because what's the fourth derivative?
0. Well, wait.
No.
Sine
in
x.
general, sine x. I'm back.
Just going to repeat again.
Right, it's going to start repeating. Now it's going to start repeating. So I have to stop. And then as Chris was saying, it's going to go 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. Now the idea is how to write it. So how to really write this. So let us watch carefully the writing. So f of 0 is, so sine x will be equal to, f of 0 is 0. Sorry. Yeah, f of 0 is 0. F prime of 0 is 1 times x. So we're going to have an x. The second derivative is 0 times x squared. Then it's minus 1 over 3 factorial x cubed. Okay, and then the x4 we're gonna have a 0 as we realizing, and then it's a positive term, the pattern, but now it's gonna be 1 over 5 factorial x to the power 5. I'm gonna write 2 more terms, and then I'm gonna write in sigma notation, and then so plus 0, 1, and then it's a 0, x6, and then it's a negative x7 plus so on and so forth. So that's really what's going to happen. Now let's write this in sigma notation. So actually, before I do that, of course, the 0 will go, so I'm going to be left with that. That's the sign of x. All right. So what's this in sigma notation? Okay. Okay, give me write sign x in sigma notation. I want to watch the powers very, very closely and write it using sigma notation. First, let us watch the powers that they are going to show up. Which powers are showing up here? X cubed, x5, x7. So the power that x is going to have are which powers?
Odd powers.
Odd powers. Don't be afraid. Odd powers. How can I write an odd power? Because here I cannot write xn. It doesn't work. Because if I write xn, how I'm going to reflect the idea that I have zeros for coefficients. It's hard for me. So I cannot write xn. So what, because only the odd power showed up. So I'm going to write it here. What are the odd, how can I write odd numbers? Do you remember how?
2n minus 1.
To n minus 1 or to n plus 1? Because even are 2 times something. That's the even. To get the odd, you have to add 1 or you take away 1. It doesn't matter. Any of them would work. So let us say I added 1. Now I'm taking care of the odd powers. Then, of course, here we see that we have 3 factorial, 5 factorial. So we're going to have here to n plus 1. It's the same as the powers. Now my n start from 0 all the way to infinity. Because if n is 0, I'll get x over 1. If n is 1, I'm going to get 3 over 3. I meant 3 factorial here. My apology. If x is n equal to 2, I will have x to the power 5 over 5 factorial and so on. I still have to take care of this alternating sign, plus, minus, plus, minus. And we know that the only way we take care of the alternating sign is to take it minus 1 to a power n. And then I check, is my n correct? Or I need n plus 1. So I'm going to stop here and check what I have so far. If n is 0, minus 1 to the 0 is a 1 over 1 times x. I'm picking up the x with a positive sign. If n is 1, I'll have minus 1 over 3 factorial x to the power 3. So I am on the right track. So we write this down. So sine x is equal to x minus 1 over 3 factorial x cubed plus x to the power 5, etc., etc. In sigma notation, it's sigma minus 1 to the n, x to the power 2n plus 1 over the quantity 2n plus 1 factorial. So the sine x will only involve the odd power of x. And this is going to work the interval of convergence. It means for which x's will this equality hold. If we find the interval of convergence for this series, it will be like e to the x, and it will converge for all values of x. It means this equality will hold regardless of whatever x you put here, those are going to be equal to each other. Okay, so that's the power series of the sine of x. And the terms, this one is the tangent line. This one is what we're going to call the cubic approximation, and then the quintic approximation, and so on and so forth. And that's how we write sine x. How we use this, actually, the most important idea that people use this is that once you know the power series and you're working with the sine x, you actually start using, a lot of time what people use is like the first degree Taylor polynomial or the third degree to approximate the sine. So as I said once before, people memorize the series, and then when they are working with the sine of x, they say, okay, I'm going to approximate it by x. If they need a better approximation, they move forward and say, okay, let me approximate it with the first two terms. If they need even better, they can at most approximate it with the first 5 terms. So those power series are really used to actually work with the function sine of x. All right, I think my time is up. Try to do the homework. You may struggle with it. Don't worry about it if you cannot do the problems. Tomorrow we're gonna keep doing along the same line. So we're gonna find the power series or the Maclaurin or the Taylor, which basically mean the same thing, of more and more functions. Okay. Any question before I let you go?